Oh, hello and welcome. This is SFU Math 152, Calculus 2, Brenda Davison. Today we are going to talk about section 7.8, improper integral. So when we were doing the strategies for integration, improper integral sort of popped up there unexpectedly, and I alerted you to the fact that we would get more information about this coming, and now that day is here. So we are going to look at two types of improper integrals. Let me just first say that I absolutely love this book. If you want to, it's an interesting book about the Indian mathematician, fascinating life, amazing mathematician, and a really well written and engaging book about him. Highly recommend that that you find that book and read it. Okay. What we're going to try to do is evaluate the area of a region bounded by 1 over x squared and y equals 0 and y equals 1. Okay, that's going to be this thing right here. These words here are, this is this problem right here. Y equals 0 and x equals 1. What? The curves, hang on, I think I'm lying to you. Let me sort this out. These words here, 1 over x squared. Oh, I see. Y equals 0 and x equals 1. Oh, I see. Sorry. These words here is not this picture here. These words here is this picture here. So it's going to go going like that the whole way. Can we figure out what that area is? Okay, that's what we want to see if we can do. So we're going to just start by taking a look at increasing the distance over which we're integrating. So first we're going to try to integrate from 1 to 2, see what happens. Then we're going to go from 1 to 3, then we're going to go from 1 to 5, and then, whoa, we're going to see if we can go from 1 fully the way out to infinity. Okay, so this one, we know how to do these things. This one here is the integral from 1 to 2 of 1 over x squared dx, and that's going to be minus 1 over x evaluated at 1 and 2, and that's going to be minus a half plus 1, and that's equal to a half. Okay, so that's picture A. There's picture A. Okay, what about picture B? Picture B, it's going to be the same integral, except the limits of integration are changed. Now we want to see what happens when we go from 1 to 3 of 1 over x squared dx. And that is going to be minus 1 over x evaluated at 1 and 3, and that's minus a third plus 1. And so that will get me 2/3. Okay, and then similarly, this one is going to be, this one, I'm going to call it C here, and C, that's going to be the integral from 1 to 5 of 1 over x squared dx, and I evaluate that and I get 4/5. So the area here is 1/2, then the area is 2/3, then the area is 4/5. What am I going to get to? Well, maybe I'll get to 1. I mean, it sort of seems to be somewhat approaching 1. Is that the case or not? So that's what we're going to do here, is evaluate. First, what we're going to do is evaluate an integral where the interval over which we're going to integrate is infinite. And that is an improper integral of type 1. So if we have an integral, here it is, and carefully note here the limits of integration. So we have an integral going from a to t, and it exists for all t bigger than a. Then what we're going to do is say that the integral from a to infinity is the limit of this integral here as t gets arbitrarily large, provided the limit exists. So if the limit exists, then we're going to say that the integral exists, and we can assign it a number. Similarly, if we go in the other direction, if it exists for all t less than b, so now the t is down here on the lower limit of integration, then we can take the limit as t goes to minus infinity, and we have the same thing. If the limit exists, we call the integral convergent, and if the limit does not exist, we call the integral divergent. if we have the situation where we are going from minus infinity to infinity, like this, we were evaluating an integral and both of the endpoints are growing arbitrarily large in absolute value, you split that into two any place you want. So I've split it at position A. It doesn't matter. 0 is oftentimes quite convenient. So split anywhere, and then evaluate each one of the two as above. And you need to have that both of them to be convergent. Then the one that's got two infinite endpoints, this guy here, it exists and has and is equal to the sum of the two pieces. Okay, split anywhere. Often 0 makes calculating easier. I find it really easy to multiply by 0. I find it easy to add 0. So I often pick 0. Okay, let us take an example and see what happens. We're going to first look at, well, we're going to look at two improper integrals here. The integral from 1 to infinity of dx over x and the integral from 1 to infinity of dx over x squared. Okay, so let's do this one first, b, because that is the one, in fact, that we already had on the front as my first example, where we're sort of getting a feel for what's going on. So let's do the proper job about evaluating this one and see what happens. So we have a situation we're being asked to integrate, or and which basically means geometrically to find the area under the curve 1 over x squared between 1 and infinity. So what we do is we move the stuff about infinity off into a limit, and instead we integrate from 1 to t. So t is just it's a number, and we're saying, okay, let's evaluate this integral between 1 and t, and then we'll let t get arbitrarily large. So that is going to then look like this, the limit as t goes to infinity. Now I'm going to integrate just like I always would. It's going to be minus 1 over x evaluated at 1 and t. So then that is going to be equal to the limit as t goes to infinity of minus 1 over t plus 1. That is the evaluated at the upper limit minus the lower limit. And then I simply take this limit. So now this is a calculus 1 problem, taking limits. Taking limits never goes away in calculus. You cannot dispense with them. So we're going to attempt to evaluate that limit. And so you can see what happens when t gets really big. 1 over t goes to 0. So this limit is 1. So that means the limit exists and it's 1. So therefore, I would say that the integral from 1 to infinity of dx over x squared is convergent. And furthermore, I could write that the integral from 1 to infinity of dx over x squared equals 1. Okay, we're going to do them all like this. So it's another example. Let's take the integral from 1 to infinity of dx over x. Excuse me. And so what we're going to do, same thing. We're going to put the problem with infinity. We're going to voice that out into a limit. And so we have this here at 1 to t. Okay, so I've replaced that upper limit of integration with t, and it used to be infinity. I replaced that with t, and then I'm going to take the limit as t goes to infinity. That is dx over x. And then that's equal to the limit as t goes to infinity of log x evaluated at 1 and t. And that's going to be equal to the limit as t goes to infinity of log t minus log of 1. Log of 1 is 0. And then what is the limit as t goes to infinity of log t? That is infinite. The log function becomes infinite when the argument of the log function approaches infinity. Okay, therefore the limit does not exist. And we would then say that the integral from 1 to infinity of dx over x is divergent. Okay. There is no value that we can give. I want to point out something to be careful about, and that is you notice that the limit as x goes to infinity of 1 over x and the limit as x goes to infinity of 1 over x squared are both 0. Okay, so in both these cases, the integrand approaches 0, 1 over x and 1 over x squared. Okay, so they both approach a 0. But when we integrate and look at the area underneath, one of them is convergent and one of them is divergent. Okay, we're going to see this for sums as well. So, for example, if we're coming later in this course, another preview, something to look forward to. We're going to come later in this course to infinite sums. So we will see at that point. If I were to do a discrete sum, I would add up all the numbers, the 1 plus a half plus a third plus a quarter, whatever. That looks actually in some sense, this thing looks like, looks like this integral from 1 to infinity of 1 over x dx. And indeed, this sum is divergent. As well as this integral. We just showed that integral is divergent. It turns out to be, and we will see coming, that this sum is also divergent. Similarly, I could look at this. Well, we just showed that this integral is convergent. And we know what this is. What did we find that answer to be? We found it to be 1. So then we could ask this kind of a question. What is the sum from 1 to infinity of 1 over n squared? That would look like this. That would be like 1 plus a quarter, 2 plus a ninth plus a 16th. So this is the sums of the reciprocals of the squares. Oh, and this is very exciting. It's a spoiler alert here. So this is it's convergent in the same way this thing is convergent. This is convergent, but it's much more difficult in these discrete sums sometimes to figure out to what does it converge. And this one is a famous one. We will come to this later. I find this an amazing result. It's pi squared over 6. So look at that. We have the square numbers, and then pi shows up. And also 6, which is the first perfect number. Oh my goodness, it's very exciting. Okay, so we're going to see that we're going to be able to use these improper integrals to talk about infinite sums later, a major sized preview of what's coming. Okay, let's take a look at a couple more of these improper integrals. Let's do C here. And now what we're going to do is when we start to look at these things, we're going to do this with the sums too. We're going to look at the integral. Before we do anything, we're going to try to get a sense of, do we think it's going to converge or not? So let me just state a fact here for you. That is, we will actually show this in gory detail, but I'm going to state it as a fact right now. That is the integral from 1 to infinity of 1 over x to the p. So p is a number, dx. This is convergent if p is greater than 1. We'll go through that and show that to be the case, but that is an important fact. Okay, so if that, we just saw the case right here. This is the case when p equals 1 and it diverged, and then this one here is the case when p equals 2 and it converged. And in fact, if we had, this is telling us if we had an integral that looked like this, from 1 to infinity of 1 over x to the 1.0001 dx, that would in fact converge. It's amazing. Just so slightly different from 1 over x, and that makes all the difference. Okay, so what we're going to do is we're going to look at this, and we're going to I'm thinking to myself, okay, does this thing converge or not? I'm going to basically try to develop some intuition. And developing the intuition means that when I look at them, I'm going to commit to making a a feeling for it, I guess, if you like, and then I'm going to see if I'm right or wrong. And if I'm wrong, I'm like, okay, so that I didn't land on that. Let's see how I could have thought about it differently. And I'm going to do that every single time, so that when I get one of these improper integrals, or more importantly, when I get an infinite series, I'll look at it. I'm going to get a feeling right off the top, whether I'm thinking it's going to be convergent or divergent, and that was going to help direct me into what to do in certain circumstances. Okay, so I'm looking at this one, and I'm thinking, okay, x is going to get large, and I'm thinking, what does this look like? So it looks like 1 over the square root of x for, well, I'm going to put it this way, in fact, for large x in absolute value. I'm caring too much about the minus sign. I mean, I'm going to minus infinity, and I got minus x. Okay, so I'm thinking, okay, what does this kind of look like? It kind of looks like 1 over the square root of x, like this little 1 here is make a big difference when x gets big. Okay, so that means it looks like 1 over x to the half. So I'm expecting this thing to diverge. And now I'm going to proceed. But I've committed. Maybe I should be committed. Okay, this is the integral we're doing here. We are going to invoke the proper limit notation here. That's going to be the integral, so t to 0. Okay, so this is the problem, if you will. I replace the problem with t, and then I put the limit going to minus infinity. Okay, now I go ahead and integrate. So I'm going to have here limit as t goes to minus infinity. I integrate, I get minus 2 square root of 1 minus x evaluated at t and 0. And so that then I'll put those endpoints in. That's going to then be the limit as t goes to minus infinity of minus 2 plus 2 minus the square root of 1 minus t. And now I'm looking at this limit, and I'm thinking, okay, I've got a square root function just grows arbitrarily large as its argument grows arbitrarily large. So there you go. This thing is infinite. The integral diverges. And I feel all happy because my intuition was correct. Okay. The integral diverges. So we're not always going to get a number out. Okay, let's take a look at D. Okay, before you hear me say it, commit. Look at it and say, wonder, does this look like it will converge or diverge? And first, also notice that both the limits of integration are arbitrarily large. Okay, so I'm looking at this and I'm thinking to myself, for large x, so I'm looking at this guy here, and it's dx over 1 plus x squared. And I think for large x, what is going to happen? It looks like when x is like 10 billion, it doesn't really matter. 10 billion squared plus 1. I don't really care about the plus 1. So it looks like 1 over x squared. And then I think to myself, aha, that is p greater than 1. Therefore, I'm going to guess that this thing will converge. Okay. All right. Also, I've got the issue that I've got both of these becoming infinite. So I'm going to split it into 2 and handle that separately. I'm going to choose to split it at 0. So I'm going to write this as the integral, the limit, as t goes to minus infinity. Now, this is going to catch the bottom half. And then the integral from 0, oops, mistake. I need also the limit as t goes to infinity of 0 to t dx over 1 plus x squared. Okay, so I've split it into 2 at 0. I've captured the part about infinity into my limit notation. It's the same integral, of course, but I will evaluate it twice. And I have to evaluate it twice, so because if it's convergent, I won't get the right answer if I don't. So I'm going to say here, this is the limit as t goes to minus infinity. And what is the integral of 1 over 1 plus x squared? That, folks, is the inverse tangent. It's one of those ones you have to recognize. And I'm evaluating that at t and 0. And then I have the other one here. I'm evaluating that at 0 and t. Okay. All right. So that's going to be the limit as t goes to minus infinity of the arctangent of 0 minus the arctangent of t plus the limit as t goes to infinity of the arctangent of t minus the arctangent of 0. And that is going to be what? Okay, what is the arctangent? Let's draw a picture of what the arctangent function looks like. This right here is minus pi by 2, and this here is pi by 2. So the arctangent of 0 is 0. Oops, let's get rid of that. The arctangent of 0 is 0. And now I'm taking the limit. I'm taking this limit as the t approaches minus infinity on the arctangent, and that is going to, this is going to be minus pi by 2. And then over here, I'm going to do the same thing. I'm going to, this part here, the tangent as t approaches infinity, the arctangent of t approaches pi by 2, and then the other one is 0. Okay, I add those two things together and I get pi. I mean, this is kind of cool too, because look what's happened. We've got a graph like this, and the graph that we have is f of x, that's the integrand, 1 over 1 plus x squared, looks like this. So when x is 0, this thing is 1, and then it goes like this. It looks like this. It goes out there like that, and we have now figured out that the area under this whole thing going all the way plus and minus infinity, that area in there, that area is equal to pi. So yeah, we've got pi coming up in a place in places where we may not have seen it, not necessarily so tightly tied to the circle. All right. Let's see what else we can do with this new skill of handling problems with infinity in integrals. And so here we are. Now we're going to try to evaluate the area of the region bounded by these curves. Let's draw a picture of what this looks like. So the curves are 1 over the square root of x. That looks like this. And y equals 0. So that's here. X equals 1. Put that right here. So that's this continues, but this is x equals 1, and x equals 0, which is the y-axis. So that's my I don't, I'm happy with that. It's too scribbly. Okay, so that is x equals 0 is this line right here, the y-axis. Okay, so we're being asked for the area. So we're being asked for this area here. Okay, so we're not having the interval of integration going from minus infinity to infinity. What we're doing is having the area under this. We have basically a vertical asymptote in the interval of integration. Okay, so this is x equals 0 here, and x equals 1. You can see that what's happening when x is equal to 0, we have 1 divided by 0. The integrand becomes infinite. So be careful. Like these are easy to miss. So I am here like this. It's okay. It's obviously an improper integral if you see an infinity here or here. I mean, you can like go, okay, I can see that. Here, now that we've introduced this idea of having the possibility of a discontinuity in the interval of integration, what we're going to have to do is every time we get asked to evaluate an integral, we're going to have to look and say, is this thing are we going to experience problems with this thing anywhere between 0 and 1? And if the answer to that is yes, then we cannot just brush that under the carpet. We have to say, okay, this is an improper integral, and we will have to deal with that appropriately. So here, there's a vertical asymptote at x equals 0. What does that mean? That means this: 1 over square root x becomes infinite at x equals 0. This is a problem that we must address. Okay, and let's see how we do that. It's very similar to what we did before, just harder to recognize the problem when you first observe the integral. So here's our question. And so what we do is we recognize that the problem is 0. And so we're going to take the limit as t approaches 0 from the right. So we're thinking of, kind of sort of starting here and then moving this way. So we're going to take the limit as t approaches 0 from the right, and we're going to integrate from t to 1 of 1 over square root x dx. Okay, now that I've sort of put the problem out here, this is just a straightforward integration. So I just keep that limit there, limit as t goes to 0 from the right, and I integrate, and I get 2 root x evaluated at t and 1, like that. And that is going to be the limit as t goes to 0 from the right. And I do this, that's going to be 2 times the square root of 1 minus 2 times the square root of t. And when t goes to 0, this simply goes to 0. So this is equal to 2. So this integral converges, and its value is 2. So this is an improper integral of type 2. Okay, let's just have this detailed out here. The function is continuous on the half-open interval AB. It's discontinuous at B. Then we remove the B, we replace it with a T, and we put the problem here into the limit. And if the limit exists, then the integral exists, and it converges to whatever value that the limit converges to. Okay, if we have a half-open interval like this, and it's discontinuous at A, then the discontinuity is here. Then this is like the example we just had. Then we remove that out to the front, and we replace the A with the T there. If we have a discontinuity in the middle somewhere, then we separate at the discontinuity. So I'm going to put that here, split at the discontinuity. Split it at the discontinuity. So the discontinuity is at C. I split the integral at C, and I have two different integrals that I'm going to then handle, and each one of them has a discontinuity at C, but I refer those back to these two cases above. We just discussed how to do that. So it's similarly like when we had this minus infinity to infinity, we said, okay, split it and do it in 2. And we're going to do exactly the same thing here. When the discontinuity is in the middle of the interval, we are going to do it in 2. Okay. So you must notice where the problem is. You cannot blindly proceed without taking over the problem. Otherwise, well, you'll go down in flames is what will happen. Okay, so let's take a look at this first one, A. We want to, we're going to here look at the integral from 1 to 2 of dx over x minus 2 squared. So the first thing to do is look at the integrand and say, is there a problem with any of x values between 1 and 2? Yes, there is. The problem is at 2. So the problem is at 2. Okay. So we are going to then move the problem out into a limit. So this will then be the limit as t goes to 2 from the left, and we'll go from 1 to t of dx over x minus 2 squared. Okay, it's easy integral. So we just proceed to integrate. We have to keep that limit notation in there. limit as t goes to 2 from the left, and we integrate here. We get minus x minus 2 to the minus 1 evaluated at 1 and t, and then we do that algebra there, and we get this 1 over t minus 2 minus 1 over 1 minus 2. That's clearly a number. So we just need to look at this thing here and say, oh, what happens when t approaches 2? Well, what happens when t approaches 2? That thing blows up. Okay, so this thing does not exist. This is, or it's not equal to, but so this limit doesn't exist. So therefore, the integral is divergent. Okay. All right, next one, B. The integral from 0 to 2 of dx over 2x minus 1 to the 2/3. This is even trickier because there's no problem at 0, there's no problem at 2. Where is the problem? So you're going to always have to look and say, is there a problem? Does the function not exist for some reason anywhere in between in the interval 0 to 2? And yes, there's a problem here. Problem is where? It's at x equals 1/2. There's a problem at x equals 1/2. So we must split the integral at 1/2 and deal with this with them separately, and they both must independently converge. Okay, so what we're going to do here is write this like this. The integral from 0 to 1/2 of dx. That's not very clear. Let me make that nice half there so we can see what I'm doing. Okay, so I'm going to go from 0 to 1/2, and that is going to be dx over 2x minus 1 to the 2/3. And then I'm going to go from 1/2 to 2 dx over 2x minus 1 to the 2/3. Okay, and I'm going to, now I mean I have the same, I'm going to now solve the same problems I just did right here. I'm going to put it into a limit, and then I'm going to integrate both of them, and then I'm going to take the limit, and I'm going to see what's happening. Okay, so I'm going to write this out with the proper limits put in. So this is then what is going to be the limit. This one here is going to be the limit as t goes to 1/2 from the left of the integral from 0 to t of dx over 2x minus 1 to the 2/3. And then this one is going to be the limit as t goes to 1/2 from the right of t to 2 of dx over 2x minus 1 to the 2/3. Okay, so now I've got two improper integrals written out with proper limit notation, and the problem is at the end point of the integration. Okay, so I'm gonna, there's a few steps here. Please do the integration and substitute in t and substitute in the t and the 0 and the 2, and so I'll just put an additional step down here, the actual limit that we end up having to take. That is going to be 3/2 to the times the limit as t goes to 1/2 from the minus side of the cube root of 2t minus 1 minus the cube root of minus 1 plus the limit as t goes to 1/2 from the right, the cube root of 3 minus the cube root of 2t minus 1. So it's looking like this limit's going to exist because this, when t gets to be 1/2, is just 0. So is this, when t is 1/2, that is simply 0. So we are left with this guy here and this guy here. So this is going to be equal to 3/2 1 plus the cube root of 3. Okay, so the integral exists and it has a value, and we have found the value. So that is part B. There's a few details missing, so stop the video, fill in details. In fact, you may want to just start right from the beginning yourself and go through without looking what I've done, and make sure that you can do this. Okay, there's another one here, C. I'm going to just do the same thing. I'm going to fill in some of the details, make sure the key new steps are identified for you. So that the question C here is to ask, what is the integral between 0 and 1 of log x dx? Okay, well, so the problem is at 0. Can't take the log of 0. So the problem, we identify where the problem is. So we're going to isolate the problem out here into the limit, and we're going to have this here, 2 to 1 of the, sorry, t to 1 of log x dx. And then we need to be able to integrate log x dx. We have done this in a previous video. Let us just reclaim that information. So that we went by parts. U equals log x, du is equal to dx over x, and dv was equal to dx, and v is equal to x. And that allows us to integrate this guy, and we find out that it's x log x minus x. Okay, so that is the integral of log x. I'll be using that right here. So this will be the limit as t goes to 0 from the right of x log x minus x evaluated at t and at 1. So I am going to then do a bit of algebra so I'm evaluating this integral at 1 and at t. I still haven't taken the limit yet. I'm going to do a little bit of simplification. Again, there's a couple of steps I'm missing here. Please do those yourself. I get this thing here. Okay, so let's see, when t goes to 0, I see that I'm not going to have any trouble here. However, here, I need to understand what's happening here when t goes to 0. I have basically of the type 0 times infinity, right? This is indeterminate form. We're going to need to use L'Hopital's rule. So now this is the time to remind yourself of that if that has not stayed in your mind from Calculus 1. Okay, we're going to L'Hopital's rule. And to use L'Hopital's rule, we want to see an indeterminate form of 0 over 0 or infinity over infinity. This is 0 times infinity. So I'm going to rewrite that. I'm just caring about this right now. I'm going to rewrite that limit. The limit as t goes to 0 from the right of log t over 1 over t. It's because now I have the form infinity over infinity, and then I can take the derivative of the numerator independently of the derivative of the denominator. So I'm going to get 1 over t here, and then here I'm going to get minus t to the minus 2, and then that is going to be, let's see, limit as t goes to 0 of minus 1 over t, and that's just simply, sorry, it's not minus 1 over t. That we've got 1 over t divided by 1 over t squared, which is t. So that's going to be 0. So that thing goes to 0. This thing here goes to 0, and that leaves us with that minus 1. So I can now write out the answer. The integral from 0 to 1 of log x dx is equal to minus 1. Okay, that's the improper integrals. There's one other important technique or piece of information we're going to use to sometimes just decide if something is convergent or divergent. Maybe we don't care exactly what the number is, but we want to know, does it converge or does it diverge? And sometimes it's hard to tell, and what we will sometimes do in order to make it easier to figure out what's going, we will invoke the comparison theorem. Okay, so here is the comparison theorem here. We have two functions, f and g, and g is smaller than f, as shown in the graph, over the entire area that we're going to want to integrate. Now, if the bigger one is convergent, then something smaller is convergent. That's statement 1 right here. If something smaller is divergent, then something bigger is divergent. That is the statement here. Okay, it's easy to mix it up. Okay, so watch that you maybe even draw a picture in your head. I know sometimes students will have this and then they will have the reverse conclusion here. So it's easy to mix up. Okay, I'm even gonna write that. It's easy to mix up the inequality direction. Be careful. Possibly draw a picture. Okay, let's see how we can use this thing. We have this comparison theorem, and let's see how we can use it. Here's how we're going to try. We're going to do two examples of using this. Okay, so now this is when really our intuition about what's going to happen is even more important, because if we think it's going to converge, we're going to have to start looking for something bigger that converges. If we think it's going to diverge, we're going to have to start looking for something smaller that diverges. So you have to kind of have an inkling of which way you're going. So let us look at the first one. It's the integral from 4 to infinity of dx over log x minus 1. Okay, so I'm thinking to myself, does this converge or does this diverge? So what should be coming into my head is I know what happens, for example, to this. This I know already from before diverges. Now, does x grow faster than log x or not? Yes, it does. So I'm thinking that especially when x is large, 1 over x grows faster than log x. Okay, so then I am thinking, okay, this thing is likely to diverge. So then I think to myself, okay, this thing is likely to diverge. I want to find something that is bigger that diverges. This is the thing about the comparison theorem. You need to orient things the right way. So let me just draw a little bit of a graph here, looking like this. Here is y equals x, and here is this value here is e, and this is y equals log x minus 1. Okay, so how am I going to do this? Then this is how I'm going to be thinking. X is greater than or equal to log x minus 1 for x greater than or equal to 4. Okay. That means that 1 over x is less than or equal to 1 over log x minus 1 for x greater than or equal to 4. So and then I will consider this integral, the integral of from 4 to infinity of dx over x, and I can do that quickly. That's going to be the log of x evaluated at 4 and t, and that diverges. Okay, oh, I lost the limit. Shoot, let me fix that. That's careless. The limit as t goes to infinity of log t minus log 4. Okay, and that, when I take that limit, that's infinite, so this diverges. Okay, that diverges. So now what do I'm gonna, how am I thinking? I'm thinking I have something that diverges. So now I have here is bigger than this. This thing diverges, and this is bigger, so therefore it diverges as well. So therefore this integral diverges. And I did not have to integrate this function. In fact, it does not integrate in terms of elementary functions, so I could not have done that. But just to figure out whether it diverges and converges, I don't have to be able to integrate it. Okay, so let's take a look at the next one. This is going to be the integral from 1 to infinity of e to the minus x squared over 2 dx. Okay, I'm going to employ my usual thing, commit. Do I expect it to converge or diverge? I think that e to the minus x squared, it decreases extremely quickly. So I'm expecting convergence. So my intuition says I expect convergence. Okay, so what do I do? I expect convergence. I can't integrate this in terms of elementary functions. I expect convergence. So then what I want to do is look for something bigger that converges. This is the what I'm using this intuition, so that I'm going to look for something bigger that converges. Okay, if I can't find that, then maybe my intuition is wrong. If I can find that, then I'll show that it converges. Okay, so you have to kind of make a commitment of what you're doing. So I'm looking for something bigger that converges. Okay, the next thing I'm going to do is I'm going to write a series of inequalities. Inequalities are hard. It is very, very easy to confuse yourself, and it takes a lot of time, I think, to develop a skill with these things. It's something that I'm still finding I have considerable room to improve on these things as well. So do not be surprised if it takes you a certain amount of time thinking about the inequalities and get mixed up at which thing is bigger and which thing is smaller and what are proper legal moves, etc. like that. It is a skill that takes considerable time to develop. Okay, so I'm going to make some statements here, and that's the first statement I'm going to make is e to the x less than or equal to e to the x squared over 2. Okay, I'm looking for something bigger that converges, and I know I can integrate e to the minus x. Okay, but starting like this because I can see, and this statement actually, I have to be very careful. This is actually true for x greater than or equal to 2. I know there's a 1 here. I'm going to fix that problem later, but this inequality is only actually true for x. Well, it is for sure true for x greater than or equal to 2. It is actually not true for x equals 1, so I need to be careful. Okay, then I reciprocate on both sides, and then I change the direction of the inequality when I do that. And this is again for x greater than or equal to 2. That means e to the minus x is bigger than e to the minus x squared over 2 for x greater than or equal to 2. So now I have something bigger. There it is. I was here looking for something bigger that converges. I have found something bigger. Now I will check if it converges. Because I have here, this inequality is true only when x is greater than or equal to 2, I am going to go from 2 to infinity of e to the minus x dx, and I'm going to find out this is very easy to do. This is the limit as t goes to infinity of the integral from 2 to t of e to the minus x dx. It's an easy integral to do. Limit as t goes to infinity of minus e to the minus x evaluated at 2 and t. And that is going to be the limit as t goes to infinity of minus e to the minus t minus e to the minus 2. And that's 1 over e squared. Okay, I have found something that is bigger that converges. Yay. However, I'm not totally finished because I didn't do it from 1 to infinity. I did it from 2 to infinity. But let's think about it. Where do the troubles in the world come? They come in the tail. I mean, it doesn't matter what integral I have, like this. If I take a finite piece, this will be finite. If there's no discontinuities in the function, e to the minus x squared over 2 is nicely behaved. It's continuous. from 1 to infinity. So any piece that I select out is going to be finite. So what am I trying to say here? I'm trying to say I was originally trying to look at this integral here from 1, and that is e to the minus x squared over 2 dx. What I'm going to do is split that up into 2, not for a reason of a discontinuity, just because I know something about it from 2 to infinity. So I'm going to go from 1 to 2 of e to the minus x squared over 2 dx, and then I'm going to go from 2 to infinity of e to the minus x squared over 2 dx. Okay, what do I know? I know that this one here, this here converges by comparison with this. And this is finite. It's some small little slice of area. It's finite. So great. I'm taking some finite number with some other finite number. I don't know what either one of them are, but when I add a finite number to another finite number, I get a finite number. So that means, therefore, this guy, the original thing I cared about, converges. Okay, so you got to be careful with the inequalities, careful setting up the comparison theorem, and then sometimes you have to, in fact, maybe just look at a certain portion of it to see what's going on. That is a very tricky question, that last one. Okay, that is our section right now on improper integrals. We will be back next time, and I'm going to do some, we're going to start talking about the differential equations. All right. I will be back. Thank you.